And we're going to change the word so that it fits your final exam. Instead of use a graphing calculator, we're going to change this to without a graphing calculator. In fact, without any calculator, we're going to graph y equals log base 8 of x. Well, again, you're graphing a log, you need to know what the basic log graph has. You need to know that every log graph has an asymptote at x equals 0. Every log graph goes through the point 1, 0. And since we're graphing log base 8 of x, our other point will be 8, 1. So there's our basic log graph. Does it have any intercepts? Yes, an x-intercept at 1. What's the equation of the asymptote? It's a vertical asymptote at x equals 0. Domain and range. The domain are the x values are bigger than or equal to 0, and your range is everything. So that's really quite straightforward to graph your basic log graph. And then what happens, and if you want to turn to page 400, we're going to do a couple of other examples. Then what happens is that you're going to be asked to take everything you learned in your transformations unit and apply it to your logs unit. So you're going to be asked to graph something like y equals 4 log base 3 of x plus 1 plus 5. And the beautiful thing is it's not any harder than anything else you did in your transformations unit. But what you have to be able to recognize when you see this equation, just like you had to recognize in all the other equations that we graphed, is what's our parent graph? What's the base graph that we're starting from? So here, off to the side, I'm going to just write my parent graph is a log graph. What's the base of this log graph? It's a log base 3 of x. And I'm going to take out my highlighter, and I'm going to highlight log base 3 of x in my equation, just so I remind myself that that's part of my parent graph. The 3 is not a transformation. What does my log base 3 of graph look like? Well, all log graphs go through 1, 0. This one will go through 3, 1. It has an asymptote at x equals 0. There's my parent graph. We've got 2 key points and an asymptote. How did we do our transformations unit? Well, we looked at our equation from left to right. We said, hey, there's a 4. What does that 4 do? Vertical or horizontal? Vertical. Vertical stretch. You're going to multiply your y values by 4. Keep moving from left to right. Notice I'm going to skip over that 3. That 3 is part of my parent graph. It's not a transformation. The next thing I run into is this plus 1. It's inside my function. It's going to be a horizontal translation, and it's going to move 1 to the left. And then finally the plus 5 outside of the function, vertical translation 5 up. So how did we set this up in our transformations unit? We said, okay, I have the point 1, 0, 3, 1, set up 2 sets of arrows, stretches and compressions first. Well, the only stretch I have is y by 4. Translations, 1 to the left, 5 up. So what happens to 1, 0? It stays 1, 0. What happens to 3, 1? Multiply y by 4, becomes 3, 4. 1 to the left. This will be 0. this will be 2. 5 up, this will be 5, this will be 9. What happens to our asymptote? The only thing that's going to affect a vertical asymptote is if you translate it left and right. Do we go left and right? Yes, we go 1 to the left, so our asymptote will be at x equals minus 1. Once you have your new asymptote and your new points, your graph, start with your asymptote. We have an asymptote at x equals negative 1. We have a point at 0, 5, and a point at 2, 9. With the asymptote, and you know what the shape of a log graph is, we can now graph our function. Can you see how this is identical to what we did with everything in our transformations unit? The tricky part is you have to know what your log graph looks like, which isn't that tricky. It's not that hard, okay? Other things that can be complicated is to know that that 3 is part of your base function, so it's not a transformation. But if you highlight what's part of your regular function, you're not going to make that mistake either. We're going to do one more graphing example. Here, the hardest one I can think of. There we go. Why is this one hard? Well, it's a natural log, which shouldn't make it any harder, but does. So you have to know that your parent graph is y equals the natural log of x, which, just like every other log graph, has x equals 0, a point at 1, 0, and what's the other point? E, 1. Same shape. And so we're going to have 1, 0, E, 1, and our asymptote at x equals 0. Just getting things set up to start with. Now normally, before I even start doing that, I would go from left to right and label things. What's the 2 going to do? Vertical or horizontal? Vertical stretch. You multiply your y by 2. What about the 1/2? It's inside the function. Horizontal. Horizontal stretch. Going to multiply x by 2 over 1. We do the reciprocal of that number. Why also did I make this question a little bit harder? Because you have to remember to factor it. It's not in factored form. So we're going to take extra time to write it in factored form. Remember, whenever you have horizontal stretch compression with a horizontal translation, you have to write it in factored form. What does factored form look like? We have to pull out that half. Now, I find that students, as a student and for students, pulling a half out of 2 is hard. But it's not hard to think backwards and say, if I had pulled out a half, this half would have to multiply that number to get 2. And if you think that way, can you see it's really easy to see that this number is 4? But trying to pull a half out of 2, it's not as easy to imagine right, I'm going to get 4. Right, here's a real-life application of pulling a half out of 2. You've got a 2-liter bottle of Coke. You want to pour it into half-liter or 500 ml bottles. How many can you fill up? 4. That's pulling a half out of 2. But this is much easier to think of it this way. Oops. And so what are we going to do? We said we're going to multiply y by 2 and x by 2. We're going to go 4 to the left and 3 down. So our first point, 2 comma 0, and multiply by 2, 2e comma 2. 4 to the left, this will be negative 2. This will be 2e minus 4. There's nothing more you can do with that unless you go to decimals. And then 3 down, minus 3, minus 1. Finally, our asymptote. The only thing that's going to affect an asymptote, moving left and right, we're moving 4 to the left. X equals minus 4. So now we can go sketch our graph. We have our asymptote at x equals minus 4. Plot our points. We've got negative 2, comma negative 3. And we've got 2e minus 4, comma negative 1. Well, remember that e is 2.7. So if you're going to do an estimation here, 2 times 2.7 is 5.4. 5.4 minus 4 would be 1.4. So I'm going to go to approximately 1.4 comma negative 1. I'm going to label that point 2e minus 4 minus 1. Just connect your dots. The shape has to match the log graph. And so this one is harder because we had to do the factoring. It's harder because we have to keep the number e in the question all the way through. But other than that, it's exactly the same as every other transformation we've done so far. Okay? It's usually at the end of this unit that people, if they look back on how they did on transformations, are like, by now you're like really, really, really good at all of your transformations. You're like, oh, why did I make so many mistakes on that test? All right, you can do 8, 9, 10, and 11 for practice.